Hi, in this video, I'm going to talk to you about scale reliability and validity. The context of this topic is itemized rating scales. Itemized rating scales are one of the most widely used forms of scales for measuring various constructs in the social sciences in general and marketing in particular. Typically, this involves developing a set of questions that people can respond to on a 1 to 5 or 1 to 7 scale, and combining those responses into an index called or an index of some sort. So typically, a multi-item scale involves a stepwise process. You develop a theory. From there, you generate a large number of items, either by brainstorming, looking through secondary data, or conducting focus group type interviews with the target audience. You reduce the number of items to a reasonable number using qualitative judgment, and then based on that, you go and gather data, perform statistical analysis, purify the scale, gather more data of a different sample, evaluate scale reliability, validity, and generalizability, and finally you get a scale. The bottom line here is that developing a multi-item scale involves a number of steps, which conclude in assessing scale reliability and validity. For this reason, it is always best to use a pre-existing scale than attempting to reinvent the wheel. As far as possible, find a scale that somebody else has conducted tests of reliability and validity on, one that has been used in the past, was tried and tested, and go with that. It is only in circumstances when what you're trying to measure is new to the world should you think about generating a new scale. Even in those scenarios, I would recommend modifying an existing scale or adapting an existing scale. Many years ago, I constructed a scale of attitude towards a website. This is in the early days of the internet. Rather than starting afresh, I decided to adapt existing scales on attitude towards websites, consumer websites, and attitude towards the ad, a TV commercial or ad. So rather than starting completely afresh with a clean slate, I adapted an existing scale to develop a new one. Let's understand now the issues of reliability, validity, and generalizability. Reliability refers to whether the scale generates the same result from one instance to another. A very good example would be a measuring scale. So when you step on a weighing machine to check your weight, you might measure once and then feel a bit unsure about whether that number was the right number or not. You might then step on the scale a second time and a third time. To the extent that the numbers are pretty much in line, the scale is reliable. In this case, the weighing machine is reliable. Thus, reliability is a measure of consistency of the scale. This may be assessed many different ways. One is by testing and then retesting like you would in a weighing machine. Another would be finding alternative forms of measurement. So in one case, you use one scale. In another case, you'd use a different measurement form, and then you kind of see if those correlate. If they do, then you've got some sense of reliability in your scale. A third metric most commonly used is the measure of internal consistency. As it turns out, in the world of surveys or descriptive research in general, one doesn't have the luxury of doing retest reliability. Consider this. If I'm not sure about whether my scale is reliable or not, I could go and ask my respondents the exact same question I asked them in the last iteration of the survey. And just to be sure, I could send the survey out to them a third time, have them respond to it a third time. So if the numbers for the first survey, second survey, and third survey all are close together, then I would assess my scale as being reliable. Now, in practice, using retest reliability is just not realistic. because it is hard enough to get a respondent to complete a survey once. Having them complete the same survey a second time and a third time is near impossible. Therefore, in practice, what we do is we give our respondents a set of items that are very closely related. Consider an example. Here is a scale that I'll read off the items to you. This was a scale that, excuse me. Okay. I thought I had a scale available with me, but I don't have one available with me to read off the statements to you. So I'll just give you my sense of a good scale of how that would play out. So let me just do this. So one example would be, if I want to understand how happy somebody is with the restaurant, I could have them ask them 3 questions, give them 3 statements, such as, I like the food at the restaurant. I enjoyed my meal at the restaurant. I loved the food at this restaurant. All 3 items are more or less saying the same thing. They're assessing the respondent's attitude towards the food at the restaurant. Now, I could have asked this with just 1 question, but instead I decided to ask it with 3 different questions to assess the internal consistency of my scale. If in fact these items are measuring the same issue, which is attitude towards taste of the food in the restaurant, then the responses to the 3 questions should be very similar or highly correlated. In other words, if somebody responded on a 1 to 5 scale 4 for the first item, then they should do the same for the second and third as well. To the extent that the items all are highly correlated, one would then say the scale has high internal consistency. So here's some more about reliability. Reliability formally can be thought of as a measure to which the scales are free of random error. If the level of random error is 0, the measure is perfectly reliable. I just went over test, retest, and alternative forms of reliability and internal consistency reliability. In all cases, we're trying to find some way to assess the level of reliability, basically to see if the random error is 0 or not. One metric commonly used in measures of internal consistency for reliability is known as Cronbach's alpha. Cronbach's alpha ranges from 0 to 1. It's a measure of correlation across all of the different items, all of the different statements or items. If this number is below 0.7, we generally deem the scale as being unsatisfactory and not reliable enough. If the number is about 0.7, then we say the scale is reliable. On to validity. But before I examine the slide, let me go back a few slides to the idea of measurement accuracy in general. So our scale is accurate when XO, the observed score for our measurement, is equal to, in practice, our observed score consists of the true score, the systematic error, and random error. We would know our scale is a good scale when the other 2 values, XS and XR, are 0. So XR we know is a measure of reliability, is a measure of random error due to lack of reliability or unreliability of the scale. And we're going to look at now XS, a measure of systematic error in our scales, and understand what that is. So let me use the same example I shared with you a second ago about the weighing machine. So imagine, again, you step on a weighing scale and you measure yourself once, twice, third time. You're probably going to see numbers that are not exactly the same, not identical. This is what random error is. The fact that from one instance to another, the numbers could be off by a little bit. The error is, of course, random. Now, so this is a true story. So I was measuring myself in the gym, and this guy walks by saying, that scale is wrong. I was like, well, what do you mean? He said, the scale always, it overestimates your weight. Like, okay, that's good. Good to know. It's like, and why are you measuring yourself? Well, it's okay for me if it consistently overestimates my weight, because all I want to see is my weight from then to now. So let's say my weight was my true weight is let's put some numbers to this thing, is 175 pounds, and the weighing scale says 185 pounds. Right. So I go again, I measure another day, it is 176. Of course, the true weight may have been 186. Now, all I'm interested in is really the fact that my weight has gone up or gone down. Right. And this is the, of course, you have here the true value and the observed value. Now, the true value is, and the observed value are out of sync, of course. There's a 10-pound difference between them. This is a systematic difference. That means from one occasion to, whenever I measure my weight, there'll always be a delta or a difference of 10 pounds here between my true weight and the observed weight. That's a systematic error in the machine. And that's, of course, a challenge to validity. Right? Of course, my response to this friend was that I don't really care, because all I care about is the fact that my weight has gone up or down. All I care about is the difference here. And that's my focus. I don't really care as much about, what the true value is. But okay, hopefully that makes sense. In any event, so we have here identified then systematic error in this example, and in the previous example identified what random error was. So let's see what validity is. A scale is valid when not just XR is 0, but even XS is 0. And therefore, as you can see, for a scale to be valid, it must not only have no systematic error, but also not have any random error in it. In other words, reliability is a requirement for validity, formally stated. Oops. I'm looking for the slide where I have that information, and I can't locate it right now. But reliability essentially is a necessary but not sufficient condition for validity. In other words, a scale must be reliable in order for it to be deemed valid. But just because it's reliable doesn't automatically mean it's also valid. There are many forms of validity that have been examined, and these include measures like content validity, which is a subjective but systematic evaluation of whether the scale represents the thing it's being designed to measure. There's another one called criterion validity, which measures whether the scale is related to other variables as it would be expected to be related. Construct validity measures whether the construct is measuring what it was supposed to measure. Conversion validity is a measure of the extent to which the scale is related to other measures of the same construct. Discriminant validity is a measure of how the extent to which the scale differs from other scales that it's not supposed to be related to. And nomological validity is a measure of how well the scale correlates with other measures, measures of different but related constructs. Okay. Let me wrap up this section then with an example. So many years ago, let me give some background here. Arbitron for many years has been entrusted by advertisers to measure radio listening behavior of people. For the longest time, they used diary panels. So if you listen to some music on the radio, you'd make a note about what song you listen to, how many times you listen to it every single day. And this is how data was gathered for the longest time by Arbitron. After Nielsen bought out Arbitron, they decided to switch from a diary panel to a portable people meter. This is a cool little device, which if you're familiar with the app Shazam, it's going to Shazam songs. So it's going to pick up the audio signals and songs, and based on the audio signals, it'll figure out not just the song, it'll pick up the song, the type of song, and so on. Now, so it turns out that the portable people meter worked for the most part, but it didn't work so good at picking up jazz signals. So now imagine somebody is riding their car and their phone, or he has the portable people meter app going on, or they have an actual device in their car. The portable people meter will pick up the rap songs they're listening to, the hip hop, pop, rock, and all. It'll pick it up accurately, but it did not pick up jazz signals too well. Okay. So what turns out is that after PPM arrived, it turned out that they were measuring and looking at how much people were listening to on the radio, and they noticed that radio listening was dropping across the board. And when they dig deeper into what was going on specifically, they noticed that it was not the people listening to radio less across the board, but it was the drop was more so for certain kinds of music. Right, so so you look at this here closely. After PPM was introduced in San Francisco, there's a little bit of a change here. In Tampa Bay, a big drop in jazz listening. In Vegas, about the same. In San Diego, a little bit of a drop you're seeing from up there to down here. Chicago, a bit of a drop, and then LA remaining about the same. So what we're seeing then is in many places, the switch prompted a drop in jazz listening behavior. And this isn't a real effect, this is a measurement effect. In a sense, there's a validity issue here. The PPM wasn't measuring jazz quite as accurately as it was measuring other genres of music. And therefore, there's a systematic drop in listening behavior as measured by the PPM. Okay. So here's that slide I was looking for earlier and I couldn't locate. So relationship between reliability and validity is as follows. If a measure is perfectly valid, it is also perfectly reliable, because validity means both XR and XS are 0. If a measure is unreliable, it cannot be perfectly valid, right? Because again, reliability is a necessary but not sufficient condition for validity. Okay, to wrap up then, we've examined in this video we've examined reliability and validity issues in itemized rating scales. Thank you for joining me.